chapter 9, get through that, get that done, and then I have both tests we can still give out. Whether you want to see them or not's another story, but I do want to give them back so you guys can look at them. I will say what I've done with chapter 9 from this. If you've read chapter 9 or are going to attempt to read chapter 9, it is extremely complex. Okay? Extremely complex. Short chapter, but extremely complex. So what I've done is I've kind of taken my own John spin to it to somewhat simplify it to the important concepts that you guys need to know right now. So some parts of this slideshow might not necessarily appear specifically laid out this way in the chapter, but I think for simplicity's sake, it'll be easier going through the lecture, going through the PowerPoint. Now you can always reference back to the chapter, of course, but I think trying to get the meat of what the chapter is trying to tell you or teach you is what I'm going to do here. So we've talked about oxygen delivery, oxygen transport. This one's about carbon dioxide transport. So again, we've talked about oxygen delivery, getting oxygen from the lungs to the tissues. We talked about oxygen delivery being how much oxygen is delivered in milliliters per minute. 1,000's delivered, but how much does the tissues consume? 250 mLs of oxygen. Again, where do we carry most of the oxygen in our bloodstream? Hemoglobin, the rest being found where? Dissolved in blood plasma. So again, oxygen, most of it bound to hemoglobin, the rest of it dissolved in the blood plasma. Alright, so now let's talk about carbon dioxide. We know cells need energy, ATP, to function. Of course, it needs oxygen to help do that. But after metabolism has occurred, we know there's going to be a waste product. After cellular metabolism has occurred, there's going to be a waste product. And what is that waste product? Carbon dioxide. So carbon dioxide will be released from the tissues. The more the tissues have to work, for example, with exercise or exertion, the more tissues that have to work, more carbon dioxide would be produced. Again, right now, we're not working too hard. We start running up and down the steps. Of course, I'm going to start with that, needing more energy, needing more oxygen to the cells, and I'm going to end up producing more carbon dioxide. I think of it like carbon dioxide is the trash, and we got to take it out. And what ultimately takes out the trash? Our breathing, our ability to ventilate. When we exhale, what are we exhaling? Carbon dioxide. We're eliminating that waste product. So don't forget, when the tissues function, the waste product is carbon dioxide. That carbon dioxide has to find its way from the tissues back to our lungs for us, again, to exhale. If the body's not able to do that, then we end up with all this added waste, CO2, in our body, and our body does not like that. So being able to ventilate, to exhale, to remove that CO2 is crucial. It's very, very important. Again, some of the numbers, we talked about these numbers a little bit before, but this chapter is focusing on CO2, carbon dioxide. The body at rest produces around 200 mLs of CO2 per minute. Not to be confused with the 200 number that we talk about with oxygen. Average tissue CO2 level around 46. We know with gas diffusion, where arterial CO2 is around 40, venous CO2 is also around 46. Again, moving from high pressure into low pressure. So what's the difference between, or the gradient between tissue CO2 and that CO2 that's found in arterial blood? It's a very small, narrow gradient or narrow window, only about 6 millimeters of mercury. Whereas we said oxygen takes about 60 millimeters of mercury of oxygen. CO2, there's a very small difference between arterial and tissue or even venous CO2. Alright, so normally when we ventilate, when we're exhaling, we're removing CO2 at the same rate it was produced. Okay? If I produce more, what am I going to change? I'm going to change how much I ventilate. So if my CO2 level rises, what will I ultimately do? I'll ventilate more to try to get rid of that CO2. So alveolar, again, big A represents alveolar. Alveolar and arterial CO2 is still around 40 millimeters of mercury. The terms hypo versus hyperventilation, again, we intentionally alter our ventilating pattern. By definition, specific definition, you know, on the test questions, I like to take those definitions verbatim and then ask that question. So hypoventilation occurs when CO2 production momentarily exceeds CO2 elimination. That's hypoventilation. Your CO2 being produced by your tissues is rising higher than you're able to ventilate and exhale. Meaning, what's happening to the CO2? You are retaining it. This could be from less ventilatory work. Maybe it's the patient who's received too many CNS depressant type medications. We've suppressed their ability to ventilate, or they've taken something illegal that could suppress their ability to ventilate. Those patients would be hypoventilating. CO2 is being produced more than the patient can eliminate. When that state happens, it causes higher blood acidity levels or acid levels. We call that state an acidosis. Now, when we finish chapter 9 today, next week we'll do chapter 11. Chapter 11, after chapter 11, we'll step out of the textbook for a few lectures, and I do mean a few lectures to go over arterial blood gas interpretation. We'll come back to the term acidosis and what it means there. So this is hypoventilation. Hyperventilation is when the rate of CO2 elimination momentarily exceeds the CO2 that's being produced. Now, normally when we think about someone hyperventilating, how do you picture them breathing? Really fast, really fast. They're ventilating, they're moving, they're removing lots of CO2 because they're breathing so rapidly, or deeply, or a combination of both of those. So, leads to more ventilatory work. The patient is moving lots of air. They are removing lots of CO2. They're eliminating that CO2 more so than it is being produced. That creates the exact opposite of an acidotic situation or an acidosis, and it causes blood pH levels to rise, which is an alkalosis. Again, we'll get into acidosis versus alkalosis more when we start talking about blood gas interpretation. Again, and that actually will start next week, blood gas interpretation. Even though my schedule doesn't show that. I'm just telling you right now, we will be talking about blood gas interpretation next week. Beginning to anyway. All right, so oxygen and CO2 transport. I love this picture, I love this animation because it's really showing how oxygen and CO2 transport really fundamentally functions. So our lungs provide the oxygen that our tissues need. All right, our lungs are providing the oxygen our tissues need. So our tissues can do their thing, right? Again, this guy's running, so he needs oxygen. As his muscles, as his tissues are working, this increased metabolism, what is he producing? Carbon dioxide. That carbon dioxide that has to return back to the lungs for the patient to do what? Exhale. And again, continue to start this process, always constantly occurring. Oxygen, of course, is going in to supply the tissues, the organs, the muscles that need that oxygen to perform their work. The byproduct, carbon dioxide, the waste product, does have to be brought back to the lung for us to exhale, and exhale that carbon dioxide. All right, so specifically, bouncing back. So specifically, how does the CO2 get from the tissues back to the lungs? All right, specifically. Anybody want to give me a very generic way? How does the CO2 get back to the lungs? Through the blood, very good. Through the blood, requiring the heart to pump that blood. Not only does the heart have to pump the blood to the tissues, to the body that needs it, but it also has to pump that blood back to the lungs, back to the heart, and back to the lungs to be eliminated or exhaled. So Here's how specifically in the blood CO2 is transported. Again, before I get into it, just a reminder, oxygen's transported in what two ways? Bound to hemoglobin, that's most of it, and dissolved in blood plasma. That's oxygen. CO2, a lot of similarity, but there is a little bit difference. All right, so it's carried three ways. CO2 carried three ways in the body. One, bound with hemoglobin. We've heard that story before, right? Except the percentage is not nearly as high as oxygen. It's also carried as bicarbonate. HCO3, bicarb. Also carried as bicarbonate. The third way, in plasma. Again, we've heard that story before when it comes to oxygen. So that's how it's carried, one of three ways. Bound to hemoglobin, as bicarbonate, and in blood plasma. That's where CO2 is being carried. All right, so let's start with the easiest one, plasma. Okay? Approximately 10% of the carbon dioxide you are carrying right now in your bloodstream is dissolved in your blood plasma. So that's a bigger percentage than oxygen, right? Oxygen, we said it was only around 2%. This is around 10% of the carbon dioxide you're carrying is dissolved in blood plasma. As CO2 leaves the tissue, about 10% of it becomes dissolved in blood plasma. All right, everybody okay with that one? How much? What percentage? 10% of CO2 is dissolved in blood plasma. So that means if 10% is taken, what's left? 90. 90% of the CO2 then will enter the red blood cell. 90% will enter the red blood cell. About 20 of the 90, 20% of it will be carried as by the hemoglobin. 70 will be carried as bicarb. All right, so 10% in plasma, 20% with the hemoglobin, 70% is bicarb. Okay, so don't get the oxygen percentages confused with the carbon dioxide percentages. Okay, add them all up, there's 100%. There's all our CO2. Oh, sorry. All right, everybody okay? So 90% of that CO2 enters the red blood cell. 20% of it specifically bound to hemoglobin. 70%, and I'm going to go over this whole confusing, convoluted looking thing in just a second, but ultimately, I'm pointing to it right there, there it is as bicarbonate. All right, everybody okay so far? Not too complicated yet.
Next slide.
Operative word, yet. Then you get to this thing, okay? And I'm going to try to keep it super simple, try to be anyways. And you guys ask me questions. Don't let me just leave it alone if it's still not clear. I know it can be a little confusing when I'm going to say it the first time, but we'll get there. It's not that bad. It doesn't have to be that bad. All right, so what I'm explaining now is ultimately how CO2 is carried as bicarbonate, okay, as HCO3, bicarbonate. When that carbon dioxide enters the red blood cell, enters the hemoglobin, it immediately combines with, what's H2O? Water. Okay, immediately combines with water. From there, now you have H2CO3. We call that carbonic acid. Carbonic acid. H2CO3, carbonic acid. As it continues, okay, and the reason it forms so quickly into carbonic acid is because of this particular enzyme known as carbonic anhydrase. It's only found in the red blood cell. It's not found in the blood plasma. That's why we say the reaction is 13,000 times faster in the red blood cell than in plasma, because this enzyme is not found in blood plasma. It's only found in the red blood cell. So, CO2 and water combine because of this particular enzyme. They form, what is this again? Carbonic anhydrase. Now that carbonic anhydrase will continue to break down. So it's H2CO3. To get to bicarb, we have to get rid of one of these hydrogen ions. And so it will split a single hydrogen ion, and what's left is bicarb. So when ultimately CO2 entered the red blood cell, it went through these chemical changes to ultimately give us bicarbonate. And that's how the CO2, 70% of the CO2 we're carrying ends up being carried as part of bicarbonate. Now, here's that bicarb in the picture. I know the picture's a little bit far, but if you have the slide, there's that bicarb. Bicarb, this little negative symbol next to it, I gave it the negative symbol here. I always forget to, just for lack of habit. It's a negatively charged ion. It will leave the red blood cell. Still is bicarb, but that bicarb will leave the red blood cell. It will shift outside of the red blood cell. So what happens now, we lose this negatively charged ion that was in the red blood cell. Well, the body wants to maintain electrical neutrality. So since we lose a negatively charged ion from the cell, something has to take its place. Chloride, normally found out here in the blood plasma, also a negatively charged ion, will then enter the red blood cell, taking that negative charge, replacing that negative charge that was lost. That bicarb that left the red blood cell, now you have chloride entering the red blood cell. And we call that the chloride shift. So here's the term chloride shift. That's chloride now entering the red blood cell because the bicarb left the red blood cell. Ultimately, remember, what are we talking about here? CO2 being transported. And how is the CO2 transported? 70% of it being carried as bicarb. Also, you may hear the term hamburger phenomenon. It was named by some Dutch scientist with the last name Hamburg. And that's where, not the food hamburger. Definitely not a hot dog, no. Nor a hot dog. All right. The rest of it, 20% of it, is going to be bound and left in the hemoglobin. We call that CO2 bound to hemoglobin carbaminohemoglobin. Careful with the verbiage here, right? What was it when hemoglobin's carrying oxygen? What was that word? Oxyhemoglobin. Hemoglobin carrying oxygen, all right? Carbaminohemoglobin is CO2 being carried by the hemoglobin. But don't get confused. Hemoglobin carries what percentage of the oxygen total? 98% of the oxygen. But of the CO2, it's only around 20% of the total CO2 being carried in hemoglobin.
Does the hemoglobin have to proceed for the carbon dioxide by oxygen?
Correct. So they don't take up the same 4 seats that oxygen does. And so one doesn't truly influence the other as far as coming on board. I will get to an example where, okay, but something happens to one, something does happen to the other. I'm not getting there just yet. But generally, no. The oxygen has their place on the hemoglobin, CO2 has their place.
Nothing like affinity or something. It's just there.
I don't want to get too far ahead of ourselves yet. Generally, no. But I will share a couple of examples here at the end where, and you use the catchword, affinity can be altered with oxygen and CO2. But we're not there just yet. Okay, we're not there just yet. So CO2 does not interfere with oxygen being transported across and getting to the hemoglobin. Right. And I like the seat example. CO2 has different seats than the seats that are dedicated for oxygen. All right. Again, what is all this important for? This is how the body carries and transports carbon dioxide. 10% of it with the plasma, the remaining in the red blood cell, amount in the red blood cell, but of that remaining amount, 70% as bicarb, 20% with the hemoglobin. So make sure you remember those percentages specifically. All right, so now that it's in the blood, now CO2 is in the blood, heart's going to pump that CO2 back to the lungs, where CO2 now, again, higher concentration in the venous side than in the alveolus, and CO2 will easily pass into the alveolus for us to do what? Exhale and get rid of that carbon dioxide. And then we can inhale, and now we're back to the previous chapter, we talked about oxygen entering and all that. This side, we're talking about CO2 being removed from the tissues and being brought back to the lungs to be exhaled. Then what happens? When that now CO2 is there at the lungs to be exhaled, remember all that process that we talked about before? It reverses. It does a complete 180 and reverses. So bicarb combines with the hydrogen ion, forms, what was this again? What's with a C? Carbonic acid, which then rapidly splits off into water and CO2. And now that the CO2 is there, where does it go? Back into the alveolus. Also picking up the CO2 that was in the plasma, also picking up the CO2 that was bound to the hemoglobin. But that long convoluted process and chemical exchange that happened when the CO2 left the tissues to go into the bloodstream, same thing happens, but in reverse to get this ultimately the CO2 out of the bloodstream and into the alveolus.
Does that water stay in the blood, or does it get exhaled?
Yes and no. Some of it will ultimately get exhaled, but most of it will stay behind there in the bloodstream. Right? So, I forgot about the chloride shift. The bicarb that was hanging out here in the plasma wasn't in the red blood cell. That has to get back in, and guess what leaves? The chloride then leaves again to maintain that electrical balance, that electrical neutrality.
Where's the bicarb? Is it in the plasma?
It's floating in the blood. It's there in the blood. Floating in the blood. Only 20% of the total is bound to hemoglobin. The rest of it, and even though this bicarb may be floating in the plasma, I don't incorporate it and say, oh, that's just CO2 freely floating in plasma, because it's not really CO2. It's bicarb. Okay? Bicarb. That's the part of CO2 transport that can get a little confusing, right? And I think it's all related to what happens here with the structure. Remember, going in, leaving the tissues, CO2 leaves the tissues, combines with water. Under that enzyme, carbonic anhydrase forms carbonic acid. That carbonic acid loses a hydrogen ion. What's left is bicarb. The bicarb leaves the cell. Chloride goes back in. There's a chloride shift. Now that blood gets transported to the lungs. Now we get back to the lungs. That process has to go in reverse to ultimately leave us with the CO2. I'm feeling it. I'm feeling it. Somebody turn the AC off in here. It got suddenly very, very hot. It's why I've taken the chapter. Because if you read through this, you're probably going to be third paragraph in going, what the H am I reading? I'm not sure what this is trying to tell me. Okay? It is complicated, but it doesn't have to be. It doesn't have to be overly complicated. All right. Let's talk about the benefits that oxygen and CO2 actually have with each other that can enhance what's going on. And hopefully that summary gave you clear explanation, and hopefully everything makes sense now, right? I gave you the shortcut, I'm sorry, you missed out on it.
Oh, that's okay.
I'm kidding. They're just as confused now as when you left, so
Okay.
don't worry. All right, so between oxygen and carbon dioxide transport, they do have mutually enhancing benefits with each other. There's two effects. I wish they were called laws. You know how fun that is to say. You know, the laws or the effects rank almost, in my opinion, right up there with those formulas, right? Another damn law, another damn name to remember. The Bohr effect and Haldane effect. So the Bohr effect is this. Hemoglobin's affinity for oxygen will decrease. Oxygen will decrease as carbon dioxide bonds or binds with the hemoglobin. So, what that means, the more hemoglobin that leaves the tissue, and again, what would cause my tissues to produce more CO2? What would cause my body to produce more CO2? Exercise. I'm going to start running back and forth here to create more CO2. As my body starts producing more CO2 from increased work, increased energy, exercise, whatever the case may be, the more CO2 that enters the hemoglobin, now how does the hemoglobin treat oxygen? Decreases its affinity for oxygen, so the oxygen goes where? Into the tissue. Causes a right shift of the oxyhemoglobin dissociation curve. I know those are the things when we went over the equilibrium curve, I said, yeah, those things don't worry about just yet, we'll get to those in due time. Well, one of them was CO2 goes up. Could shift the curve to the right. Okay, so the more CO2 produced, the more the hemoglobin wants to do what with oxygen? Get rid of it. And again, yes, the tissues are producing more because there's more work. Guess what they're going to need more help with? They're going to need more oxygen to be able to do more work. I see a hand. Go ahead.
I was gonna say, so the affinity goes down to release.
Affinity for oxygen will go
goes
down.
So the oxygen,
Can go to the tissues.
right, which is what we want.
Yeah, when we're exercising, when there's increased need, increased energy, increased metabolism, absolutely.
And if, this, I'm thinking about like the lungs, we want oxygen in the lungs, so does the affinity go up with carbon dioxide in there?
Not at the lung. Right here, we're looking at the level of the tissue and the bloodstream.
Okay,
Okay, so not so much in the lung. That amount's still going to be the same, but by that time that blood gets to the tissues that need that oxygen, from the hemoglobin piece, the more CO2 that enters that hemoglobin, the more oxygen will leave the hemoglobin. Again, to the tissues that are doing more work, more energy. And obviously, and so again, mutually enhancing effect. If the CO2 goes up, more CO2 is being produced, the more the oxygen will leave the hemoglobin and go help support the tissues that are doing obviously more energy, more work. Again, that's how it's supposed to work. You know, with disease and illness, things get all jacked up and screwed up. This is how it's supposed to work. That again known as the Bohr effect. And I'll read it one last time. Hemoglobin's affinity for oxygen decreases the more carbon dioxide enters the hemoglobin.
This has nothing to do with the Bohr equation, right? Like-
Yeah, that's different. That's different. Just making sure. Yeah. Good catch though.
I was supposed to do like with the affinity, like to carry the carbon monoxide, it has just one, it just has two bonds, this is,
Carbon monoxide
yeah.
or carbon dioxide?
No, I'm talking about the carbon monoxide
Okay.
is the one that they rather carry than the oxygen,
Correct,
right?
correct.
This one is kind of from the same family, kind of, it has two molecules of oxygen, but
Okay.
if that has anything to do with like CO2 getting into it, they would say, okay, CO2 is getting in, so oxygen get out because they'd
Right, but-
rather be with it.
But if there's, so if we're taking that example, if there's carbon monoxide here that hemoglobin really, really likes, has a very high affinity for it,
There wouldn't be any room.
it's not going to give up that carbon monoxide. It's going to, even if the tissues are producing more CO2, it's not going to want to give up that carbon monoxide. Because hemoglobin's affinity for carbon monoxide is how much more than oxygen? Like 210 times more. So it's still going to hang on to that carbon monoxide, which ultimately, even if it did give up carbon monoxide, that's not going to help the tissue at all.
Yeah, I didn't explain right.
It's okay. That's okay. We'll come back to you. Connor?
So, does carbon monoxide decrease hemoglobin's affinity for oxygen?
For oxygen,
or-
yes.
Okay.
Yes.
It's not just that its affinity for carbon
Again.
monoxide is so much more.
But again, it's because hemoglobin would much rather carry carbon monoxide than it would oxygen. You know, if both are present, hemoglobin's gonna say, no, I'd rather take the carbon monoxide and go ahead, let's leave the oxygen alone. Alright, that's the Bohr effect. Now the Haldane effect, well, let me get to this, sorry. So, the more the muscles work, I forgot my own slide. The more the muscles work, more CO2 is being produced, right? The more CO2 being produced, well, guess what? More oxygen will be released to the tissues that obviously need it for its increased work, its increased energy. Sorry, I forgot I had that in there. All right, now let's talk about Haldane. The removal of oxygen from the hemoglobin. So this is the exact same picture from Bohr. As the oxygen leaves the hemoglobin, okay, so as oxygen leaves the hemoglobin, is removed from the hemoglobin, that increases the hemoglobin's affinity for carbon monoxide. Carbon dioxide, sorry. Again, so this same effect. So now, by the oxygen leaving, the hemoglobin would say, okay, more CO2, come on board. There's plenty of room now. Okay, that's the Haldane effect. And it's where the Bohr effect and Haldane effect are mutually enhancing when it comes to both oxygen and oxygen delivery and carbon dioxide removal. Yes? No? Maybe? This is part one and only part one. There's no part two here.
Thank God.
Thank God, I'm saying. All right, so Bohr effect changes hemoglobin's affinity for oxygen to give it up at the tissues. Haldane effect changes hemoglobin's affinity for CO2. When the oxygen leaves, it'll take more carbon dioxide on board. Again, both mutually enhancing to each other. There's probably a million questions you guys have. I don't mind going back over a few things, but ultimately remember what we're doing here. Lungs are breathing in oxygen. The body's transporting that oxygen to the tissues or organs that need them. Again, carrying oxygen what way? How is oxygen being carried? Oxygen bound to hemoglobin, most of it, and the rest dissolved in blood plasma. As the organs, tissues are using that oxygen, the byproduct of cellular metabolism is carbon dioxide. Carbon dioxide enters the bloodstream as how? Again, three different ways. Bound to hemoglobin, and what do we call that? Carbaminohemoglobin. Again, careful the words here. Carbaminohemoglobin, that's CO2 bound to hemoglobin. Not to be confused with oxygen bound to hemoglobin that we call oxyhemoglobin. Not to be confused with carbon monoxide bound to hemoglobin that we call carboxyhemoglobin. You can see I already have a list of look-alike, sound-alike names for when I need those wrong answers for some of these questions. Yep, let me pull some of these in here and then I'll make up another one for a wrong answer. Again, I can see where those words can get jumbled and all mixed up in our head. So make sure you truly know what it means when CO2 is bound to hemoglobin. Again, what do we call that one? You have to question yourself. Carbaminohemoglobin. Carbaminohemoglobin. So CO2 is bound to hemoglobin. We call that carbaminohemoglobin. That's one. Carried as bicarbonate. And then what's the third way? In the blood plasma. Now, percentages wise, 10% in plasma, 70% is bicarb, 20% is carbaminohemoglobin. That delivers the CO2 through the bloodstream back to the lungs for us to do what? There goes the CO2. All right? A process so simple, but definitely sounds so confusing, right? Mic drop. And it's something you kind of have to repeat and go over again and again. Chad's video, to play it on repeat, especially those parts about the transport specifically of carbon dioxide. And don't let those other words that we talked about from previous lessons get mixed up in here, because there's way too many C words, right? Carbonic anhydrase, carbonic acid, carbaminohemoglobin, carboxyhemoglobin, oxyhemoglobin, hemoglobin, whatever, methemoglobin, all the other things related to hemoglobin that we've talked about before. that do sound somewhat similar. All right, let me give you a few questions, and then I'll be happy to entertain any questions you guys may have. And the question may be, I need to hear this again. I need to go back and listen to it one more time. All right, so what is the term used to describe when CO2 production momentarily exceeds CO2 elimination? So CO2 is being produced more than CO2 is being eliminated. What do we call that? Is that hypoventilation, hyperventilation, bradypnea, or tachypnea? That is hypoventilation. Your CO2 is being produced in excess of your ability to eliminate it. So, again, I think I've used this example before. If I'm going to hypoventilate in front of you guys right now, my body's still producing the same amount of CO2 that it always has, but if I hypoventilate, instead of breathing 10 to 20 times like I'm doing right now, now I'm only breathing 2 times. My CO2 is still building up. I haven't exhaled yet. I haven't taken a breath yet. My CO2 is still building. Finally ventilated. And now I'm not breathing. CO2 is still building up in my body. I haven't taken a second breath yet. 30 seconds later, there's breath number 2. I've only breathed twice in the last minute. So I am hypoventilating. My CO2 production right now exceeds my CO2 elimination. Next question. The majority of carbon dioxide produced by our body is transported to the lungs as A, oxyhemoglobin, B as bicarb, C dissolved in blood plasma, or D attached to hemoglobin. The majority is carried as bicarb, is carried as bicarbonate. So again, as the CO2 leaves the tissues, enters the bloodstream, some of it's dissolved in plasma, some of it's bound to hemoglobin, the rest of it in the red blood cell. But again, remember that chemical reaction. CO2 binds with water because of what's that enzyme's name? Carbonic anhydrase. It forms then carbonic acid. Carbonic acid splits off into a single hydrogen ion and bicarb. That bicarb, that negatively charged ion, leaves the red blood cell, and what enters? Chloride, and we call that the chloride shift. That CO2, bicarbonate, still SCO2 in there, that bicarbonate carried back to the body. Once it gets to the lung, then again, everything happens in reverse. The bicarb joins back up with the hydrogen ion, enters the red blood cell, the chloride shifts out of the red blood cell, back to carbonic acid again, then it splits off to water and CO2, and then the CO2 ends up in our alveolus to be exhaled. I think it's really that chemical reaction that gets so kind of confusing and difficult. The first or second or third or sixth time you hear it. In time it does get better. In the red blood cell, CO2 and water combine to form what? Is that carbonic acid, plasma, carbaminohemoglobin, or carbonic anhydrase? Carbonic acid. You can even look. If you marry these two together, that's where the H2CO3 forms. Anybody like chemistry? Shocker! I'm so shocked. I'm so surprised. Yeah, there was a reason we didn't do chemistry, right? Yeah, it's the little bit that we have to talk about here, and I do promise it's a little bit.
Are we done?
I don't know. Question? Never say never. Never say never. Probably. Very little. All right, sorry. Next question. What's the effect called when hemoglobin's affinity for oxygen decreases as CO2 bonds with the hemoglobin, or binds with the hemoglobin? Is that the Bohr effect, Haldane effect, delta CO2 effect, or carbonic acid effect? I had to make some wrong answers, you couldn't tell. This is the Bohr effect, right? Even if it comes down to a guess, I think you could at least eliminate 2 of those answer options because I made them up, right? Even if it comes down to a guess, it turns into a 50-50 guess, right? Not that I want you to guess, but if push comes to shove, you have to guess, at least you have a 50-50 shot at it. I wonder what the answer to this one is, but I'll go ahead and say it. What is the effect called when the removal of oxygen from the hemoglobin increases hemoglobin's affinity for carbon dioxide? Don't listen to Jeremy. This one is B, the Haldane effect. This one's Haldane. I know it's going to take a little bit to review this. Go back and look at the video, read through. I don't think I attached any videos to this because sometimes they can make this so much more than it has to be. And again, trying to keep it a little, and trust me, a little less chemistry than the chapter makes it out to be. But again, I know it's our first time talking about it, and welcome to the next section of stuff, right? Holy crap. I'm trying to think for a second. The last grouping, you guys are like, oh, these damn formulas. He's killing me with the formulas. This next section, I don't think I'm going to hurt you so much or kill you with the formulas. Maybe some of these words can get a little twisted up a little bit, if you will. But I'm trying to think in chapter 11, I don't think there's any math formulas per se. And blood gases, there's no math with blood gases, but it's interpretation, so you have to be able to see things and interpret them. But I think that was my last question, that was. All right, any questions from chapter 9? Your faces, bless your heart. Yes, Pat?
Is it the carbonic anhydrase that causes the reaction?
It's the reaction between the CO2 and water that forms the carbonic acid. It's because of the enzyme carbonic anhydrase.
What causes it when it reaches the lungs first?
Carbonic anhydrase. Yep. The same reaction. Just everything's going in opposite sequence or opposite order. All right. I do have tests to give back, so we're not going anywhere just yet. But I at least wanted to I wanted that chapter to be over with, if you couldn't tell. So we have plenty of time to talk about the test questions. All right. Any questions? Both.